Hello students! Topic 30 is on linear inhomogeneous systems. In this section we discuss solving first-order linear inhomogeneous systems of ODEs with a constant coefficient matrix, as given below. Vector x prime equals matrix A that has only constants times vector x plus vector f, where vector f is not the zero vector. So again, I'm stressing that this is inhomogeneous versus homogeneous. If this vector here was 0, then this system would be a homogeneous system. In general, we can establish a trial particular vector solution x sub f of t using the guide established for the method of undetermined coefficients when solving second-order inhomogeneous ODEs. Fill in the table below. So I'm going to fill in this table using using the guide that we had for doing the second-order inhomogeneous ODEs. Now, suppose any component of your vector function f is a polynomial of degree k. So this case right here. Then your trial solution x sub f of t should include a polynomial of equal degree with vector constant coefficients. So it should include the following: vector coefficient times t to the k plus vector coefficient times t to the k minus 1 plus etc. down to vector coefficient of t plus vector constant. So your trial solution should include this entire thing if any one component of this inhomogeneous vector function here is a polynomial of degree k. If any component of it is e to the at, then your trial solution should include some vector constant coefficient times e to the at. Now this a and this a are not the same thing. This is a vector a, this is a different a, not related, not referring to the same thing. And if, however, this trial structure matches the general form of one of your homogeneous solution forms, then we would have to do an adjustment here, similar to what we had to do with the second order inhomogeneous ODEs. However, in this unit, we're not going to cover such cases. In other words, we are not ever going to have a conflict of our inhomogeneous function will never match the form of one of our general solution terms from the homogeneous version. I'll explain what that means in more detail as we see an example. But in general, if you have an exponential e to the at in one of your components of your vector function f, then you need to include this in your trial solution. Similarly, if there is a cosine of bt or a sine of bt involved in one of your components of your vector function f, then what you're going to want to do is have a constant vector times cosine of bt plus a different constant vector times sine of bt. So if you have only cosine bt as one of your components of bold f, of vector f, then you do need both of these in your trial solution. And if you only have sine in one of your components, then you need to still have both of these. If you have cosine in one component and sine in a different component, remember f here is a vector, so it has multiple components. And if this is in one and this is in the other, then you need only this still in your trial solution. Of course, if this was a cosine 3t in one component and this was a sine 2t in a different component, then you would need this structure for both the 3t arguments and the structure again for the 2t arguments. And again, we are assuming that these general forms do not match the general forms of your homogeneous general solution. If they do, then we would need to improvise, and again, in this unit, I'm not going to cover such complications. Okay, so let's put this to practice a little bit. Let's say we have three examples here in this table. We have inhomogeneous systems on the left column, and I went ahead and I determined the linearly independent solutions to the homogeneous version and put those here in the second column, and then we're going to determine what the trial solution vector x sub f should look like. Okay, so if this vector here was not present, then you would just have a homogeneous system, and then you would find the eigenvalues of this corresponding eigenvectors. It turns out that you can see what the eigenvalues are by looking at these coefficients of the t in these exponentials. So 1 was an eigenvalue and 3 was an eigenvalue. And furthermore, this vector next to e to the t, this vector right here was an eigenvector associated with eigenvalue 1. And this vector was an eigenvector associated with eigenvalue 3. So here are our two linearly independent solutions to the homogeneous version of this system. And now we want to construct a trial solution for this inhomogeneous system. So look at the components of our bold f, of our vector f. There's a constant and there's a t squared. So the constant is a 0-degree polynomial, suggesting that we need a 0-degree, a constant vector in our trial solution. And the other component is t squared. It is a 2nd degree, suggesting that we need a general 2nd degree, so that includes t squared, t, and constant in our trial solution. Now, because this one here, t squared, let's do that one first. So we would have a constant vector times t squared plus a different constant vector times t plus a constant vector. This is the trial solution you would create just for having the t squared be one component of your vector function f. But the other component is constant and requires that you have included in your trial solution a constant arbitrary vector, which we already have. So I don't need to double up. I don't need to put a second one. So this alone will cover both cases, both components of our inhomogeneous vector over here. Also notice none of these are of the same form as what you see here, which is a vector times e to the t and a vector times e to the 3t. None of those match these forms, and so we don't have any complications. Now the next case, we have, again, a inhomogeneous. If this part here was not present, then we would have a homogeneous system. The eigenvalues of that coefficient matrix are -1 and 4, as indicated by the exponents here. And the corresponding eigenvectors are indicated by these vectors next to these exponentials. So if I did C1 times this plus C2 times that, that would be a general solution to the homogeneous, to just this part. But now we have an inhomogeneous component that's non-zero, so we want to construct a trial solution. Let's look at we have a constant, a 0-degree polynomial, and we have a sine of 2t. Well, the sine of 2t, let's do that one first. That's the complicated one. So we're going to have a constant vector times a cosine of 2t plus a constant vector times sine 2t. We'll need both of those in our trial solution. And neither of those accounts for having this constant. So in this constant, the 0-degree polynomial we have up here means that we need to also have a 0-degree vector polynomial over here. So we need to add a constant vector c. And that would be our trial solution. Now this last example is a 3x3 system. The homogeneous portion is just this, and the eigenvalues of that coefficient matrix are 1, 2, and 3, and corresponding eigenvectors are all revealed here by these linearly independent solutions to the homogeneous. But we do have an inhomogeneous component. There's an exponential, there's a cosine, and there is another constant. So one at a time, let's do the fact that we have an exponential. We're going to need a constant vector times e to the 4t. Now notice that this does not match any of these structures. Therefore, this alone will be sufficient in our trial solution. If this had been an e to the 3t and that matched this one here, then we would have a complication and a different way to set this up. But again, we're not covering such complications in this topic. Now let's address the fact that one of our components is a cosine of t. So we're also going to need in our trial solution a cosine and a sine with constant coefficient vectors. So a b vector times cosine t, and then plus a c vector times sine t. And that addresses the fact that we have a cosine of t component. And then lastly, we have this constant component, and we don't have yet any 0-degree constant vectors here, so we want to put a plus a constant vector d there at the end. Now, I want you to keep in mind that another way to write this, these constant vectors a, b, and c would match the dimension of the system. So this is a 2x2 system over here. So this vector a that we're referring to is a 2x1 constant vector. So it would look like this. You would have a1, a2, that's the a vector, times t squared, plus. Then you would have a b1, b2, that's your constant vector times t, and then plus a c1, c2. So really, when we are trying to figure out what these coefficients are, we actually have a total of 6 values that ultimately need to be found. A1, A2, B1, B2, C1, and C2. In this second case here, again, this is a 2x2 system, so each of these vectors A, B, and C are 2 by 1s. So again, this would be an A1, A2 times a cosine 2t plus a B1, B2 vector times sine 2t, and then plus a C1, C2 vector. We'd have, again, 6 unknowns to find, the A's, the B's, and the C's. And in this third example, we have a 3x3 system. So the A, B, C, and D in this general setup right here are all 3x1s. So we would have a A1, A2, A3 times e to the 4t plus a B1, B2, B3 times cosine t plus a C1, C2, C3 times sine t, and then finally plus a D1, D2, D3 constant vector there at the end. Okay, so this one you would have a total of 12 constants that ultimately you would have to find, and it can get quite complicated, as you can surmise. Okay, let's do a specific example. We have find a particular solution to this inhomogeneous system below. Let's take a look at this coefficient matrix and make sure that's not something in our table here. Otherwise, if it was, I could just borrow some of the work that's here, but it's not. So we are going to have to first figure out what these eigenvalues are of this coefficient matrix and just make sure we don't have any conflict with our components of our inhomogeneous vector over here. So the eigenvalues, we have to do 1 minus r, subtract r from the main diagonal, other entries stay the same, do the determinant, set that equal to 0. So we have 1 minus r squared minus 4 is equal to 0. So this gives us r squared minus 2r plus 1 minus 4, so that's going to be minus 3 is equal to 0, and this refactors into r minus 3 and r plus 1. So we have 2 eigenvalues, 3 and negative 1. So that means our general solution is going to involve e to the 3t times a vector times an eigenvector, and e to the negative t times an eigenvector, neither of which match the forms of just a constant or just a polynomial t. So we don't have any issues. So this allows us to next construct the trial form of our particular solution to this inhomogeneous system. We're calling it x vector x sub f. You might see vector x sub p in your homework, p standing for particular solution, but I like to put a subscript here to refer to this vector function right there. If I'm calling that f, then I want to put an f subscript here. That's just my preference. And in this case, well, we have the two components of our inhomogeneous term are a constant and a linear polynomial, first-degree polynomial. So if we just do a general first-degree polynomial, that will cover both cases. So we need to have a vector a times t plus a vector b. So here's our very basic trial solution for this particular case. All right, so next we're going to substitute this into the differential equation. So we're going to do the derivative and plug it in there, and then plug in that trial solution right there. So we wind up getting, now the derivative of this, since a and b are constant vectors, and therefore this t would distribute, right? Whatever this t right here would distribute to all the components of a, and when you differentiate a vector, you just differentiate component by component. So in other words, the derivative of constant vector a times t is just going to be constant vector, and the b's will all differentiate to 0. So we know that x f prime is just going to be the constant vector a. Now I'm ready to do some substitution into this. So we have the left side is the derivative of their trial solution vector, so we just get vector a is equal to, and I'm going to just call this capital A for now so I don't have to keep writing that matrix. So we have capital A matrix times vector x, and vector x we're plugging this into our differential equation. So we have vector A times t plus vector B. And then, of course, we have, and let's call this, again, call that vector F. So let me make this more formal. So this is this matrix A, and this is vector F right there. So I can use those symbols, plus vector F. Okay, so here is our system. We need to solve this for A and B that make this a true. Now, there's a couple ways of doing it. You can do it by matching coefficients, or matching coefficients of both sides, much like if you had, let's say you had 3t squared minus 5 is equal to at squared plus bt plus c. You would, to make these two sides be the same, you would equate certain coefficients. You would equate the 3 and the a. Then you would equate the negative 5 and the c. And then you would be able to conclude, since there is no t term over here, right, you would be able to conclude that b therefore is 0. So this idea of equating coefficients is going to be relevant. But we're going to do it at a matrix and vector level. So track down all the parts all the components of this that have a t. And vector f has some t's involved. Vector f has constants and t, so we may have to actually pull apart vector f. And I'm going to decompose vector f into the constant component and then the component that involves t, which is a 0 t. So put these together, you have vector f, right? You have 1t, which is exactly what we have right there. Okay, so let's just be clear that this was our vector f, decomposed. And the reason I did that is just to get the t's and constants apart from each other, because I can distribute this matrix A across here. And so we wind up with the following statement. We get vector A is equal to matrix A times vector A t plus matrix A times vector B plus this 1, 0 plus this 0, and I can factor the t out if you will, 0, 1 t. Now I'm going to gather the t terms together. There's two t terms. And then, of course, keep the terms that don't involve t separate. So we have vector A is equal to, and the t terms gathered together, and factor the t out. We have matrix A times vector A plus, and then we have this 0, 1. And all of that was times t. Right? So I gathered this term and this term together and factored the t out, the scalar t out. And then we have plus, and then I'll use parentheses even though they're not needed. And the other components are matrix A times vector B plus this 1, 0 vector. And we're going to equate coefficients. Notice that there is no t on this side, so that tells us that this coefficient has to be 0. This has to be the 0 vector when we're done. And this part, the part that has no t, has to match over here the part that has no t. So this is going to equal vector A. Okay, so this will allow us to create two different systems of equations that we can solve, first for vector A and then for vector B. Let's do the first one, solving this one for vector A. So we know that matrix A times vector A plus 0, 1 has to be equal to the 0 vector. So I'm going to subtract this vector over to this side, and it winds up looking like this. And we have matrix A times vector A has to be equal to 0, negative 1. And keep in mind that matrix A is our coefficient matrix, 1, 1, 4, 1. And vector A is our A1, A2 that we're trying to find. And so notice we just have a linear system of equations again to solve for A1 and A2. You can do this using substitution, elimination, or matrix methods. I'm going to use matrix methods. So I'm going to now write this as an augmented matrix. So 1, 1, 4, 1, equal sign, 0, negative 1. And then use row operations to put it in reduced row echelon form. So I'm going to do negative 4 times the top row and add that to the second row to change the second row. And we'll see what that produces. So that gives us top row is the same, not changing that. But we do negative 4 times 1 is negative 4, add to 4, that makes the 0 that I want. Negative 4 times 1 is negative 4, add to 1 is negative 3. And then negative 4 times 0 is 0, and then add it to negative 1, that will stay negative 1. So we get to this stage. Next I will multiply the bottom by negative 1/3. And let's see what that gets us. We have 1, 1, 0. That top row is not changing. Then we have 0, 1, 1/3. And finally, we want to get a 0 right here. So I'm going to, we also have an equal sign right there. I'm going to multiply the bottom row by -1 and add it backwards. So I'm going to use this pivot 1 right here to zero out that entry, to zero out this entry right here. And that takes us to a reduced row echelon form. Bottom row is 0, 1, 1/3. And we do -1 times 0 is 0, add to 1, that stays 1. -1 times 1 is -1, add to 1 becomes 0. And we get -1 times 1/3, add it to 0, will be -1/3. And then when we translate this back into equations, we see that A1, remember we're looking for A1, A2 here. So this stands for the coefficients of A1, this stands for the coefficients of A2. So we get A1 is equal to -1/3, and A2 is equal to +1/3. Okay, and that allowed us, that we were able to figure out what A is. Let's move that over slightly. Now let's use this second fact right here, that matrix A times vector B plus 1, 0 needs to be equal to vector A. So that would looks like this. We have matrix A times vector B plus 1, 0. That needs to be equal to vector A. Well, since we've already figured out what vector A is, we can proceed with this and solve for vector B. So we get AB plus 1, 0 needs to be equal to, and vector A, we found vector A, the first component was -1/3, and the second component was +1/3. So I'm going to subtract this over to this side, and then convert these to matrices and vectors. So matrix A was 1, 1, 4, 1 times vector B, which when written this way is B1, B2, times that vector, is equal to, and then we need to subtract 1, 0 from this vector A here. So we're going to do -1/3 minus 1, that's going to be -4/3, and we're going to do 1/3 minus 0, that'll stay 1/3. So this becomes a system now that I'm trying to solve, and I'm going to use row operations to do this again. So I'm going to write this as an augmented matrix, 1, 1, -4/3, 4, 1, 1/3. I'm going to do a lot of these same row operations, in fact, so I'm going to do some copy and paste. I believe it's exact same steps I'm going to have to do, but we will get different results in this left or right hand column here. Okay, so we do -4. I'm just going to worry about what happens here in this last column. We do -4 times -4/3, that's 16/3, and add that to 1/3, that's going to be 17/3. Then and the top is still -4/3, that's not changed. Then I'm still going to do -1/3 times that last row. So the top is still -4/3, but this will now become -17/9. And I'm still going to do -1 times the bottom row and add it backwards up to the top row. So this will be -17/9 down here at the bottom. And we have to do now -1 times -17/9 is 17/9 minus 4/3. Well, that's like doing 17/9 minus 12/9. That's going to give us 5/9. And that will be what our B1 and B2 are. So B1 is 5/9 and B2 is -17/9. Okay, and that's all we had to find, because our trial solution just had vectors A and B we had to find, and each of those vectors had only 2 components. So we found all 4 of the total components, and I'm able now to say what my particular solution is. I use the word trial when I don't yet know what A and B are, but once I know what A and B are, I call it a particular solution. It's a very specific solution to the inhomogeneous. So it's vector F sub F. This is our particular solution. It's a function of t. I'll leave off the of t though. And it's composed by doing vector A times t plus vector B. Well, I can shove all this together into one vector. So I'm going to multiply t to both components of this vector and then add that to both components of the vector B. And so we're really going to have -1/3 t plus 5/9. is our first component. And the second component will be 1/3 t minus 17/9. And that is the particular solution that we were after. Okay, now suppose that the inhomogeneous system below is n-dimensional. So this is an n by n square matrix here. If x sub f is a particular solution without initial data, so I'm just putting this parenthetical comment here because sometimes when we say a particular solution is the solution you get after you've created the general solution and you know some initial data, so you figure out what your arbitrary constants are, C1, C2, etc. And we also call that a particular solution. A particular solution is really just a specific solution without any generality. So we've been using particular solution in a couple of contexts. The result of using initial data to produce a particular solution, and also a solution without generality to a inhomogeneous system. And so that's what I mean when I say without initial data. We're referring to that kind of particular solution. Anyway, also x1 through xn, vector x1 through vector xn, are the linearly independent vector solutions to the corresponding homogeneous system. Then the general solution to this overall system is as follows. That's pretty simple. You take the particular solution that you found, and then you add it to the arbitrary constants coefficients, multiplying by the linearly independent solutions to the homogeneous system. So in this case, find the general solution to the inhomogeneous system below. Now we had already found, back here we found out what the eigenvectors were, or eigenvalues, but we never found out what their corresponding eigenvectors were, so that part is missing. So we know that R1 is 3, in no particular order. Let's just go to the 3 first. R1 is 3, so this is our first eigenvalue. We already found it to the coefficient matrix, that is, to this matrix. Now let's figure out what a vector is. Let's find out one eigenvector associated with this. So in order to do that, we have to rewrite the coefficient matrix after we remove the eigenvalue from the main diagonal. So subtract 3 from the main diagonal. It looks like -2 and -2. The other entries do not change. And then you want this to be multiplied by an eigenvector and produce the 0 vector back. You're looking for a solution to this. And we can use row operations to do this, or you can just think through it and try to think of one that'll make this happen. For example, if I have only one of those, and I would need 2 1s, right? So I'm thinking that 1, 2 might be a vector that's going to work here, right? Because 1, 1, 2, drop it down. That will give me 0. We'll multiply corresponding entries and add the results. And that also zeroes out the bottom one too. So right away, I can just see that one solution to this, we'll call it eigenvector 1, is going to be 1, 2. That'll be good enough. For the other eigenvalue was -1. So subtract -1 from the main diagonal. In other words, add 1 to the main diagonal. We get 2 and 2 on the main diagonal. The other entries do not change. And we're solving this equation. And let's see if we can just think our way through this one as well. If I do 1, 2, and -2 1s, that should zero out the top row. Will that also zero out the bottom row? Yes. So I can see that a solution to this one is going to be our second eigenvector associated with our second eigenvalue, and it's going to be 1, -2. You can also do any multiples of these, right? So you could do 2, 4 for your first eigenvector. You can do 3, 6. You could do -1, -2, etc. Same thing here. You can do any multiple of that, and that'll work. So now I'm prepared to write the particular solution we found from above. So let's just go ahead and copy that. This is our particular solution right here. And we're now ready to construct the general solution. So the general solution, vector x, is equal to, let's get the particular solution just to follow the same order as this. Let's do the particular solution first. So we're going to have this part right here. And there's our particular solution to the inhomogeneous. And then plus some constant c1 times, now let's go with our first eigenvalue with corresponding eigenvector. So e to the 3t times that eigenvector times 1, 2. And then plus a second constant times, and now let's look at this eigenvalue with its eigenvector, so e to the -t times 1, -2. And here is our general solution to the overall system. So from here, if we also had initial data, you would want to plug in that initial data and ultimately then solve for C1, C2. So there's really lots of system solving going on when you're doing this stuff. We had to do is solve a bunch of systems just to find out what A and B were. Then we had to solve systems of equations just to find eigenvectors. And then if I want to go even further and find a particular solution, if there's initial data present, then I'd have to solve a system, finding out what C1 and C2 are. So lots of solving of systems to work your way through these problems. And this is our last slide. Find the general solution to the inhomogeneous system below. Now take a look at this matrix. That's a 3 by 3. That matches exactly the matrix that's right here, which means a lot of our work is already done, because here are the terms of our, let's copy that. Those are the linearly independent solutions to our homogeneous, so that work is done. Now all we have to do is do the particular solution to the inhomogeneous. So our inhomogeneous, notice there's an e to the negative t. It's been factored out of the vector function f. So each of these would be a multiple of e to the negative t. And so we need a particular solution to look as follows. X sub f needs to be some vector a times e to the negative t. And it doesn't matter where you put the e to the negative t. And there's no complications in this, because this structure does not match any of these structures, because the e to the exponentials don't match. Therefore, we don't need any complication. This will suffice in helping us find a particular solution. Now I want to do the derivative. Xf prime. Well, a is a constant vector, so this exponential would be in every single component of a, and then when you differentiate each component, you're going to get the same thing, but the derivative of e to the negative t is going to be negative e to the negative t, and then you can factor the negative and the exponential back out of the vector a, so it just winds up being the opposite of vector a times e to the negative t. Much like it would just be if this was a scalar a in front versus the constant vector a. Okay, from here, now we want to plug into the differential equation and see what sort of system of equations we can produce. Let me move this up here. So I'm going to plug in these statements in for the x prime and the x and rewrite this system. And let's call this here vector f. And this will be, of course, matrix A, and we'll call this constant vector f, even though vector f should include this, like up here when we say vector f, that includes the exponentials, but now I'm going to say specifically that vector f is just the constant portion of that with the exponential factored out. I hope that doesn't cause confusion. And now let's substitute. So in for x prime, we're going to plug in xf prime. So we're going to have negative vector a e to the negative t equals matrix A times vector x. Well, vector x is just xf is what I'm substituting. This goes in for vector x. And we have a vector e to the negative t. And then we have plus e to the negative t times vector f. And vector f is this constant vector right there. Okay, well, I could factor out vector e to the negative t. And there's a couple ways to think about this one. If I do that, let me just copy this. Factor out the e to the negative t. Right, so this plus and this vector f that we have here will merge together, and we'll have e to the negative t out. And then if we equate coefficients, you can see right away that we need this to be equal to the negative of vector a. Right, because there's an e to the negative t and an e to the negative t, and I'm just going to equate the coefficient and this coefficient, set those equal to each other. Another thing you could have done is, because e to the negative t is non-zero always, you could just divide it away. Right? You could just divide both sides by e to the negative t to get rid of it, and then you would wind up producing the exact equation I'm about to write, which is that negative vector a has to be equal to matrix A times vector A plus this vector f that we have. Now keep in mind, we're trying to solve this for vector A. So what I'm going to do is I'm going to actually add vector A back to this side, and I'm going to subtract vector f to that side. And that is going to give us the following statement. And I'm going to write matrix A first. So we have matrix A times vector A plus vector A is equal to the negative of vector f. And factor out vector A. And when you factor vector A, you can't just put a 1 here, because this would lead to a nonsense statement, right? You can't, a plus a matrix plus a scalar is not possible. So when you factor A out of itself, it leaves an identity matrix. And of course, you'd want that identity matrix to be compatible with this matrix A. So that if you distribute, right, if you were to take this vector A and distribute it again, you would still get what you see up here. Okay, I think we're ready now to write down what this system is going to look like. So let's do A plus I. This is I3. So I3, if you recall, is a diagonal matrix with 1's down the diagonal and 0's everywhere else. And if we're going to add that to this matrix A, we just need to add 1 to the diagonal. So we have A plus I winds up being the following matrix. We have, just add 1 to the main diagonal. So we have 2, 3, 4 is the main diagonal. And nothing else should change. So 0, 4, 1, and all zeros. So there's A plus I. That's being multiplied by vector A, which is 3 components, A1, A2, A3. And this, we want that to be equal to the opposite of vector F, where vector F was this vector right there. So we have -1, 0, -2. And this is the system that we want to solve for A1, A2, A3. Again, I'm going to go with an augmented matrix, 2, 0, 4, -1, 0, 3, 1, 0, and 0, 0, 4, -2, with an equal sign implied right there. And I'm going to get 1's all down the main diagonal right away. So I'm going to just do a half times row 1, a third times row 2, and a quarter times row 3. And see what new matrix this produces for us. So we're going to have 1, 0, 2, -1/2, 0, now a third times the second row, so 0, 1, a third, 0, and then a quarter times the last row, 0, 0, 1, -1/2. Now I'm going to turn both of these into 0 using this leading entry 1 that's below it. So I'm going to do -1/3 times the bottom row and add it to the second row. And then I'm going to do, after that, -2 times the bottom row and add that to the first row. Okay, so our very next matrix, the bottom row will not be any different. We're not changing that. And a -1/3 times these zeros, add to the 0, 1. That won't change the 0, 1. That's going to stay the same. But -1/3 times 1 and then add that to a third will zero that out. And -1/3 times -1/2 is +1/6, and add that to 0. So that makes a 1/6 right here. And now let's do the -2. -2 times these zeros and add to these entries won't change those entries, so we have 1, 0 still. -2 times 1 is -2, add to 2 will make a 0. And -2 times -1/2 is +1, and add that to -1/2 is +1/2. And this is in reduced row echelon form, and we can see what our constants are. So we know that A1 is going to be a half, A2 is going to be a sixth, and A3 is going to be -1/2. Okay, so let's continue to move some things around here. Let's move that work up here. All right, so these 3 here were from the homogeneous. They're the homogeneous solutions. And we've now determined our particular solution is this vector here, where A is these components. And so we are prepared now to construct a general solution for the inhomogeneous. And that's going to be vector x is equal to, let's do the particular solution first. So I'm going to do my x sub f, but with these components. So we have 1/2, 1/6, -1/2 times e to the -t. Right, this will be, that's our particular solution, plus some constant. And now we're just going to go through these homogeneous solutions one at a time. So some constant times e to the t times 1, 0, 0, plus some constant times e to the 2t times 0, 1, 0, and then plus a third constant, c3, times e to the 3t times our vector 2, 1, 1. And there it is. There is our general solution to this inhomogeneous linear system of equations. And that wraps up topic 30.